Okay, so if you recall in our previous video, we showed that if you have a curve y equals f of x between x equals a and x equals b, and you revolve this curve about the x-axis, it generates a surface of revolution. And if you ask, what is the surface area of this surface, the answer is, it is obtained by evaluating this definite integral. So let's consider now a very simple example of the formula with a very simple or very well-known surface of revolution. Suppose we consider in the xy plane a curve that is given by a straight line y equals 3x. And we'll consider the interval from a to b being from 0 to 2. So here's our curve between 0 and 2. Of course, the corresponding y value, 3 times 2 is 6. And now, as we revolve this portion of the curve about the x-axis, we will of course generate a cone, as the curve is a straight line segment. And of course the x-axis goes through the center of this cone. So now we're going to find with this formula the surface area of the cone, but only of the outer shell, not of the base, right? This is empty now. We only get, so really think of this as these little paper cups of water. They're shaped in the form of a cone. Of course, if you want to pour water into it, the top must be missing. And that's exactly our surface of revolution here. So we just need to apply this formula. F of x, of course, is 3x, so all we need is the derivative, but of course dy over dx equals 3. So now the surface area of this cone, and if you want the sort of the classical measurements, the height of the cone would be 2 units, and the radius of the base is the length of the segment, which is of course 6. So by revolving the line y equals 3x about the x-axis for x equals 0 to x equals 2, we generate a cone without the base with a radius of 6 at the base and a height of 2. So now we can find the surface area again of the outer shell of this cone. So our surface area is, we integrate from 0 to 2 pi times f of x, which is 3x, the square root of 1 plus the derivative squared. The derivative is 3, so 1 plus 3 squared dx. Well, let's now simplify this integral and then evaluate. So what can we factor out? Well, we have 2 times 3 is 6 pi, so we have a 6 pi. This is also constant. It's the root of 9 plus 1, which is 10, so root of 10. So we factor the 2, the 3, the pi, and the root of 10, so we're left with the integral from 0 to 2 of x dx. This is now, of course, trivial. We use the power rule, and of course the fundamental theorem of calculus. The antiderivative of x is x squared over 2. We evaluate from 0 to 2, so we get 6 pi root of 10 times the antiderivative at 2. 2 squared is 4, over 2 is 2, minus the antiderivative at 0, which is of course 0. So all we have is twice of 6 pi root of 10, which of course gives us 12 root of 10 pi, or 12 pi root of 10. Doesn't matter. I'll write 12, 2 times 6, root of pi, root of 10, sorry, times pi. Okay, so now we have the surface area of the shell of our cone. And if we wanted to close up this cone and include the area of the circle, right, as the base of a cone is a circle, well, so I'll write here the surface area plus the circular base will be, well, the area of the body, what we've just found, so 12 root of 10 pi plus the area of the base. Of course, it is a circle of radius 6, so it is pi r squared. But 6 squared is 36, so all we have is plus 36 pi. And that's it. Now you can imagine that the only difference, if I give you slightly more complicated curves, is you would simply get a slightly more interesting integral. But aside from this, everything else is the same.